Hello.
Asha, good afternoon.
Good afternoon, sir. Sir, is everything ready?
Yeah, I mean, Namkar, we will start like maybe after 5 minutes, five.
Sure, sir,
I
sure.
think I can see only around 13 participants.
Yeah, yeah. Even we also noted the same, so I think we can.
Hello, can you hear me?
Yes, sir, we can hear you.
Okay.
Oh, okay. Okay, thank you very much. Can I start now?
Just a small introduction, sir.
Okay,
May I
thank
start
you.
now?
Yeah,
Okay.
you can. Thank you.
Okay. Hello and welcome to International Geoscience Colloquium, jointly organized by Christ College Autonomous Irinjalakuda, University of Kerala, University of Exeter, University of Zululand, South Africa, supported by Ministry of Earth Science. So today we'll be having the continuation of our session, Developments in Stratigraphy and Sedimentology, Big Data Analytics and Artificial Intelligence in Geoscience, Geoscience and Integrated Reservoir Modeling. With all due respect, let me invite our session chair, Dr. Saju Menacheri, to take over the session. Over to you, sir.
Thank you, Asha. That's a good introduction. Today, we are having welcome to the Virtual International Geoscience Colloquium, Session 3. My name is Saju Menacheri, together with Lindo Alapad. We are the session chairs of the technical session, Big Data Analytics and Artificial Intelligence in Geosciences. In this session, you will be listening to presentation covering the subject Big Data Analytics and Artificial Intelligence in Geosciences. Each presentation will be around 30 to 40 minutes. At the end of each presentation, you will be have 10 minutes Q&A time with the speaker. I would like to introduce you to the first speaker today, Dr. Keniso Beta, South Africa. He will be presenting on the subject on time series analysis and forecasting using a novel hybrid LSTM data-driven model based on empirical wavelet transform applied to total column of ozone at Buenos Aires, Argentina. The time duration around 1966 to 2017. Dr. Bata is a senior lecturer at the University of Zululand Geography Department. Previously, he was worked as a senior scientist at the South Africa Weather Service, Global Atmospheric Watch station at Cape Point, Cape Town, where he was looking after the instruments and also produce and quality control the data. He graduated with a PhD at atmospheric physics at Uzbekistan. He did his postdoc at the University of KwaZulu National, Durban, South Africa, at the physics department, where he helped resurrect the Durban LIDR. His research interest at atmospheric dynamics, atmospheric chemistry, remote sensing, and data science. To the audience, could you please mute your video and microphone all the time until you have the time to ask the question during our Q&A. Also, you can type any of the question in the chat box anytime during the presentation. So now I would like to welcome Dr. Bata for this talk. Could you please take over to your talk, Bata? Thank you.
Okay, thank you. Thank you very much for the introduction. I will here today present to you one of the studies we recently did with my PhD supervisor from Reunion Island, an island which is quite not far from Mauritius. If we move towards the Indian Ocean from here, South Africa, meaning it is just a few kilometers from Madagascar towards when you face towards Australia. So Reunion Island. So, but I am based here in South Africa, University of Zululand, a graduate of University of KwaZulu-Natal. My presentation will be about ozone. I studied the time series of ozone. I used LSTM to sort of do forecasting of ozone. My main aim was forecasting of ozone. The idea of forecasting of a time series of ozone came because of gaps in many of different data sets that we may have. And sometimes most of the people will interpolate, which does not bring the true reality into the data. And I then thought of developing my own LSTM model so that I can sort of model or forecast ozone. As you know, ozone is one very important composition of the atmosphere, especially if you go to the height between 20 and 25 kilometers, where it is maximum, where it forms. It forms naturally through the interaction of ozone molecules with UV radiation from the sun, and that UV radiation sort of breaks your oxygen molecules into oxygen atoms, and you'll have single oxygen atoms interact or chemically reacting with your oxygen molecules to form O3 in the atmosphere. That does also bring a situation where you have ozone destroying naturally, and it doesn't do. And so the destruction of ozone is also natural through UV, where O3 is destroyed, or O3 is broken into oxygen atom and oxygen molecules, and you have the chain goes on, formation of ozone again, and so on and so on. This process here is called the Chapman mechanism, and it should go on that way naturally, but meaning what the ozone that forms in the atmosphere is also destroyed at the same rate, not unless you have external forces sort of changing the whole system. So that's why I do this analogy of a system which is at equilibrium or steady state, where you have inflow being equal to what is coming out, so that the water within the system doesn't change, for instance, in this example of this incoming water in this small bowl here. So it is important that every time ozone must form naturally and also destroy naturally, so that you do not have the changes of ozone that are not unnatural, because then it means you'll have things like ozone depletion. Well, the ozone, for those of you who may know, is differentiated. Also, is the radiation from the sun that is responsible for creation and destruction of ozone is UV, and you have UVC, UVB, UVC, UVA, sorry, depending on the range. But in general, UVC and UVB are the main UVs that are responsible for the formation and destruction of ozone. And some of you may know how dangerous are some of these UV wavelengths. And this is just an absorption spectrum of the solar flux itself. And this is the spectrum of absorption coefficient of UV. And you'll see that most of some of the UVC is absorbed up there, and also a certain percentage of UVB is also absorbed up there. Out there. So these are the UVs that play a role in the formation of ozone. So that is my motivation. My motivation is to say, if you can measure ozone in your stratosphere, then continuously for very many years, then you may understand what is happening there. Then also you may start to be able to forecast. If you have good data, then you may be able to forecast the ozone concentration up there. So what I did is, we do here in South Africa have ozone measurement. I know you have a lot of ozone measurements also in India and many other parts of the world. We do have ozone measurements here. But I wanted to go get closer to the ozone hole and get data that is, a longer time series. That's why I chose to use data from Argentina. I wanted to get to the edge of the polar vortex and also get a time series that is much more longer. And I do note that in terms of ozone measurements around Africa, we do need a better coverage, especially stratospheric ozone and also maybe surface ozone. So the data that I use is from Banner series, and it is measured using a Dobson spectrometer. This is a Dobson spectrometer. It sort of measures UV through dividing your solar radiation into these two special wavelength, the short and wave, and you get short and long, and you get a ratio of the two that is pushed into the prism that will sort of give you the concentration of ozone, and you push that into a photon multiplier tube, which is our detector, and all the way to your data system. And this is a very quick explanation of this ozone spectrometer, but you can find more details about it in this website here. So this data that I have of ozone here. I then took that data, analyzed it, and said, okay, this data, cool, I can forecast this. If I can have a system that I can use, that I can train to sort of understand this ozone, and then it can assist me forecast the ozone, stratospheric ozone. So the system that I chose is a deep learning system, which is not like a normal neural network, but it is a recurring neural network, which falls under your deep neural network, which has actually the system where if you know the normal neural network, it will normally have a feed-forward system like this, but this recurring neural network always have this feed backwards to update the input of this hidden layer here, and also have a state so that the state is updated, and then it pushes the input of this hidden layer here together with what was updated and the state. And this recurring neural network has several gates, which will be input gates, forget gate, and all that stuff, because it must learn short-term changes in data and also long-term changes in data. It must store that, it must forget those which are not so useful. You can use that in several neurons, just like a neural network. And I just want to zoom into it and go specifically to a special type of a recurring network, which is called long short-term memory neural network, which is called LSTM. So these are best performing neural networks when it comes to time series forecasting recently, when it comes to machine learning. It is also very good in prediction of words and alphabets and so on, and also some signals like music and all those things. It has been used and it performed very well. So I chose it, and this special type of neural network, if you zoom into one of the neurons there, you have something like this. If you go into details, it has this simple linear algebra on it, and I maybe give one example of what is happening there. You have an input data, and that input data can either be fed into a forget gate, which is F, input gate, forget gate is F, and output gate is O, G is your self-recurring, and you also have internal memory, which is actually your candidate for remember or something like that, and you also have a hidden state, which assist you update your candidate for remembering, and so on. So what will happen is that it will take the input, feed it, or sort of multiply your input, for instance, in terms of the input gate, which is running here, or maybe let's make an example with the forget gate. You take the forget, your input, you multiply it with signoid. This is signoid, which is just a normal function, which shapes just like a hyperbolic function, which here is a hyperbolic function. These functions do not have anything to do with trigonometry, really. It is functions that are important in this deep learning type of thing. So you have the forget gate, which you multiply it there, and you also have your weight of the forget gate. If you are dealing with the forget gate, you have a weight of your input gate. If you are dealing with an input gate, and so on and so on. So it sort of says that if something is important, then please remember that. If something that is not important, is not important, please forget that. And it is always updating back the input with the previous output, so that you can always store that information. Of course, forget it after some time, because if you think about a human being, if a human being remembers everything that happened in life, then we will not be normal. So the system behaves like that too. It forgets everything that it's supposed to forget, and it remembers any sequence that happened, for instance, in a time series starting from 200 to 1966, like the time series that I use. What I do is I take that time series, and this is the step, this is the design of the model, of my model. I take the LSTM and put it here, but I know that if I focus my time series as it is, I'll probably get some results, but I can make it better by decomposing my time series. What I did is I decided transform, and I also compare that method with what is known by most of us here, which is called empirical mode decomposition. You can also use improved empirical mode decomposition, which is called EEMD and stuff. So my models, I will have several types of model results in here. I will have EEMD, LSTM, I will have, for instance, I can also denoise the time series before I push it into an LSTM. So I call it wavelet denoise LSTM. I also can wavelet denoise and then put that or decompose that using wavelet, empirical wavelet transform, and then push it on into my LSTM. Or I can denoise and then put it into an EMD and also decompose it using an EMD and then push it into an LSTM. Or just take a signal, decompose it using empirical wavelet transform, and then push it into an LSTM before integrating the output here, and so on, and doing my final forecast. So this is the structure that I did. And what I did is now is to say I want to compare these different types of LSTMs that I designed here. It was like about 6 models that I designed. Okay, so firstly, I had to analyze the time series itself. Of course, ozone is very seasonal, so that's why you see this these seasonal cycles here, very strong seasonal cycle here, there, and of course you will get a QBO, and because the time series is very long, you can also get a solar cycle and stuff like that. But what we note if we run it through a sequential Menkadal is that just before 1980s, we started to see declining of ozone, according to my time series here, and it goes all the way down until it starts to destabilize. Just before 2010, we're starting to see the 10 on the peak of ozone, which we are hoping that it could go back to its state. The same is indicated by yearly average or annual average Menkadal. So it means I calculate Menkadal trends for each and every year to try and see if there is any recovery of ozone. Yes, it is true. There is a bit of recovery of ozone, even though it is slower than expected. And it is observed to be a bit slower recently. When you decompose this time series, if you want to see, you take the original time series, which is this time series here, decompose it. When you decompose it, then you get these IMFs or empirical mode functions. And these are the empirical mode functions that you feed in here in a model. For instance, this is IMF1 all the way to the residual. And it means you forecast each and every IMF that you extracted from the original signal and combine everything at the end. So if you focused using empirical mode decomposition, then you get these IMFs here, and this is your residual. If you focused using your empirical mode wavelet transform, then you get all these IMFs here, and this is your residual. I noted that the empirical mode decomposition residual is much more smoother, and the empirical wavelet transform residual has some sort of peaks and so on, it is not as smooth as this one. And this told me something, that the empirical mode, the empirical wavelet residual could assist you much more better than empirical mode decomposition to get a trend of the time series. Hence, I did trend analysis of this using this method, new method that is called empirical wavelet transform. As you can see, empirical wavelet transform is the one in black. This is the first time that empirical wavelet transform is used for trend analysis. I'm comparing it with a normal singular spectrum analysis trend estimation, and I'm also putting in the empirical mode decomposition, which you need to do extra process in your time series so that it becomes a trend. For instance, you can combine your residual with the other IMFs which are closer to it so that you get something like this. And you'll note that when you look at my empirical wavelet transform, it compares far better with the singular spectrum analysis. And you will see during some years where you have much of volcanic eruptions like Mount Panatubo and all those things, the ozone reacts. You can see the recovery of ozone in recent years here in both the singular spectrum trend and the empirical wavelet transform. What I did here is also to calculate the growth rate of my ozone data, and you can identify very well here all the major events like your volcanic eruptions as well. And this is the general time series that I used from the 1966 to end of 2017. So this is what I decomposed, and this is what I extracted the trend for. This is what I use also to calculate the annual growth rate. And then my next step was to model. What I did is to train the model use data from let me put it this way. I used 70% of my data as a training time series, and I used 30% of my data as the testing time series. This that I'm showing here is the testing time series, which the 70% started from 2002, and the other data that is not included here was used for training of the model. So these results here are showing the testing part of the model itself, or what is reproduced or produced by the different models that I spoke about. For instance, empirical wavelet transform LSTM, the empirical mode decomposition LSTM. You will see that all the models do follow on the original time series, meaning if I break my time series into training and testing, I will have an original time series that I can compare my forecast with. So this was for that purpose. And when I compare all these, for instance, when I go to my Taylor diagram here, I noted that empirical wavelet transform LSTM performs far better than all other models. And I also noted that if I denoise my time series before pushing it into the empirical wavelet transform LSTM, I do lose some information. Hence, the wavelet denoise empirical wavelet transform LSTM did not perform that well. I associate that with the idea that LSTM can learn short-term variabilities and long-term variabilities. And if you denoise, you are removing some of the information that LSTM can easily learn. Empirical mode decomposition also do perform, but it is safe to note that empirical mode decomposition is a popular way of decomposing a time series, but it does not have good mathematical theory compared to empirical wavelet transform. And also here I can see, even though that it performs, but it does not outperform my empirical wavelet transform LSTM. If you use LSTM as it is, then it does not perform that much compared to pre-processing your time series before you try to forecast it. And then here I was just looking at the model performance, looking at it in terms of root mean square error and so on. And you can see here the empirical wavelet transform was performing in terms of MAE and in terms of MAPE percentage. And every time you can see that the empirical wavelet transform performed far better. In conclusion, the total column of ozone that I see over bonus series has been very stable since mid-90s. And I also note the recovery of ozone, especially when you start from 2010 towards 2017. I also associated some variabilities of ozone to different volcanic eruptions. For instance, in 2015, there's a decline of ozone due to what we all know as the Kalbuko volcanic eruption, which was quite big. We did also see the signatures of the other volcanic eruptions that happened before in ozone. And in general, empirical wavelet transform can see trend very better than the other, also the empirical mode decomposition, which means you can comfortably use empirical wavelet transform for extraction of a trend in any time series. That is a good idea because it also has a well-defined mathematical theory. And in general, I see empirical wavelet transform decomposition process as the best performing model for my forecasting of time series. My aim is to apply that into different time series. For instance, I have started to look at stream flows here. We have a lot of rivers here, which has changed over time, and we want to see how they will look like in future in terms of these deep learning techniques and so on. And this could be also applied in different things. For instance, I'm applying it on mercury measurement, gas form mercury or atmospheric mercury measurement, comparing southern hemisphere and northern hemisphere, for instance, in the time series of mercury that we have. Thank you very much, and I would like to acknowledge the National Research Foundation of South Africa. Also, the data was applied by World Ozone and Ultraviolet Radiation Data Center. I can share the website where you can get that data and so on, and some guys from Bonaseries who continue to take these very useful measurements of ozone for a very long time. So thank you very much. Is that fine? Hello?
Thank you, Dr. Betta. Thank you very much.
Yes.
It was a great talk. Now it's a time for any other questions. If anyone want to ask any question to Dr. Betta, would you please unmute your microphone and ask the question, or you can write on the chat box. So if there is, I couldn't see any other question at the chat box, or no one is going to ask. I would like to ask one other question.
Okay, yes.
Is there any relationship between the position of the sun and the degree of UV radiation into the earth? I don't know whether you noticed or you can answer that question, but I always want to understand a bit more on that question. So the position of the sun versus the UV radiation.
I think that is actually a very good question that if you, well, there are UV sensors everywhere. You mean if you look at UV at the surface?
Yeah.
At the surface, I think that could be a very good question to answer in terms of a project, looking at the level of UV in your equator, the latitudinal variability of UV and stuff like that. But with the changing angle of the sun, I will suspect that it should be possible. But I think it also depends on the amount of UV that is up there. I know that we don't have much UV like they have in southern Argentina, for instance, here, because of the ozone hole and stuff like that. So it also depends on the composition of the atmosphere at the time. But I think it could be a good dimension to sort of look at that, even though I've never thought about it myself, really.
Okay, thank you. With regards to that question, I've seen the data what you showed from 1966 to 2017.
Yes.
Some of them, there's a good peaking on the UV radiation or ozone variations. So my question is, did you notice any variation with respect to the volcanic eruption or volcanic activities or the ashes or the gas that's been sent to the atmosphere in either in Argentina or other parts of the world? So is it that to make a big difference in the UV radiation? Because as you mentioned, the composition is a main thing. So is it that noticeable with respect to Argentinian volcanic activities or the total volcanic activities around the world?
Well, what I can say in regards to that is that even though I looked at ozone up in the stratosphere, I know very well. For instance, every time when there is a major volcanic eruption, you get depletion of ozone. For instance, here the recent Calbuco volcano in Chile, which happened during our times now, because we are young people, so we were able to track it and do some research on it. You will note that ozone here was supposed to go back up, but it went back down again, meaning there was that influence of the ozone of the volcano in the ozone time series itself. However, I know that in several years, for instance, your Mount Pinatubo, your other major volcanic eruptions always do have an impact on the ozone up there. So in literature, if you go to look at literature, there are some studies that will look at ozone and volcanic eruptions and other major events that may deplete ozone. But the main thing that will deplete ozone is very stable CFCs. For instance, the slower recovery of ozone that we see now, there's a nice Nature paper that explains and associates it with some of the activities that are happening in North China, in the industrial areas there, where they continue to release CFCs and stuff like that. And that paper was published, I think, early last year or something like that. So I normally associated with that, but it would be nice it will really be nice to look at what happens to UV at the surface during these times as well. For instance, if you look at UV when there is this strong plume of Calbuco volcano, it will be nice to see what happens there.
Oh, that's good question. Good answer. Like, also, I was wondering, while especially when the volcano eruption happens, then the entire gas states can move from one place to other with all the wind directions. So again, I was always fascinated to see whether there's so much of effect on the ozone layer versus the UV radiation, all with these volcanic activities, gases emitting into the atmosphere.
Yeah, it does happen that way. For instance, a good example is that we recently published a paper where we use FlexPart to track the dispersion of Calbuco eruption and also Amazon fire. The Amazon fire that happened last year. We have about two papers that one was looking at Calbuco dispersion and the other was looking at Amazon fire distribution. I can tell you that here in South Africa, we get a lot of those particles up in the upper stratosphere and troposphere. we track that using SO2 and aerosols and all those stuff. And we could see that something that happens in Chile can travel all the way towards Australia, for instance. It passes South Africa after a few days and stuff. So
That's
what happens? Yeah. Okay.
Yeah. I mean, that's what we noticed. Like the wind direction can take from South America towards South Africa, and even that travel all the way to Australia. So I was wondering, well, our UV from Australia, especially in the month of November, December, January, the UV radiation is so high in Australia.
Yeah. Okay.
Yeah, thank you for that. There is a question in our chat box. They're asking, why are ground sensors a few meters above the ground?
Sorry?
Why are ground sensors a few meters above the ground? So Bill Wall asking the question, mentioning about the sensor, sensing on UV maybe. Yeah.
Oh, okay. Well, I may be more interested in the data and maybe know the different type of sensors that will measure whatever I'm interested in. But for instance, I know that when you measure, I've tested different heights of measuring surface winds and noticed that, you know, if you are in a different topography, then you may get a wrong value if you don't put your sensor at a proper height. But in normal basis, if we measure atmospheric chemistry at the surface, we don't go that high above the ground. Of course, if you measure closest to the ground, then you may not get the real value because of the movement of winds and stuff like that. If you want to sample air, so it's better to go a bit higher up and stuff like that. But I'm sure there are other reasons. My interest is really the data part of it, and I've not spent much time to look at why should you decide on that type of geometry and stuff like that.
Hope that's answer satisfy Bilawal. Yeah. I couldn't see any other questions in the chat box, but one of my other question I would like to ask you. You proposed one of the model. So my question is like, I mean, what is the advantage of your suggested model versus neural network model on the model predictions or to data analytics?
Well, as I said, this is a long-term short. This is an LSTM, not a normal neural network. It has a component to remember what happened long time ago and stuff like that. It can remember what happens now and remembers also what happened long time ago. I did compare this with several of the types of models that are there, statistical models, ANNs, normal neural networks and stuff like that. And this one performs far better than them. It is able to see what the other ones can't see. I also did even do hybrid, because this is actually a hybrid with this one, but I did a hybrid of statistical models and machine learning models, which are not LSTMs. And I still noticed that this one performs better. The idea is that even though long short-term memory neural network will perform better, but you need to pre-process your data before you do that. This method performs very well in different types of data set, as I tell you. I have tested it even using economics data. I'm not an economist, but I thought this I can do far more easier than the geophysical data that I normally deal with. And it works perfectly there, because with the economics data, you can even use these simple statistical models and normal neural network and stuff like that. Yeah, so that's the main thing. I have compared this with different models. When I selected the type of models that I'm talking about here, I only selected them because of their performance, really. When I use the wavelet denoised one, I know that if you remove noise in a time series, definitely you should better your forecast. But when I denoise, for instance, and take an empirical wavelet transform decomposition, then I know that I notice that an LSTM wants to see the type of noise that is in data so that it predicts it and stuff like that. So I did compare this with many different models. And if you have a question or if you want to extract a trend using this method, you can go to the literature. There is a published paper in MDPI Atmosphere about this work that I present here. There is also a few more papers who talk about an LSTM and different pre-processing methods and stuff like that.
So what is
share this? Sorry.
So what is the difference, or what is the percentage agreement with the LSTM, your model, with any other neural network model? Say 90% agree with your model, or 60% agree with your model, or big difference?
Well, I always get to 10% better than the other models.
Okay.
For instance, I'll be 10% better than the other models. Some models perform very bad. For instance, some of the guys will know about ARIMA, for instance. If you take ARIMA, you try to do a complex signal like this signal that I'm dealing with here, ARIMA will perform very bad. You will be, for instance, now.
You mute your microphone. Unmute your microphone.
Unmute. Sorry.
Yeah.
Okay. I'm saying some of you may know about ARIMA, for instance. ARIMA is one known statistical model that one can use, and other statistical models, they do not do what this one does. For instance, in a time series like this one that I dealt with here, they can go up to 50% levels, confidence levels. When I use this one, I'll be at around 87 and stuff like that, all the way up to 85, especially if a time series is not so complex.
Yeah, that's a good answer to my question. Thank you very much. And with the time limits, thank you very much for your talk, Dr. Betta. And once again, thanks from the organizing committee, and on behalf of myself, thanks for your talk. So
Okay,
next we will move to the second speaker today, Dr. Hector A. Oringo. He's an archaeologist, and he will be presenting on the subject on multi-temporal and multi-source machine learning approaches to the detection of archaeological sites over large areas. Dr. Hector is an archaeology. Sorry.
Hello. Good morning.
Yeah. Hi, Dr. Hector. Can you hear me, Dr. Hector?
Yes, perfectly well. Should I start with my presentation?
Not yet. I'm giving an introduction to you so that you can share your screen. Then you can start with. So I'll finish my introduction.
Perfect. Finish the introduction and then I'll share my screen. Thank you.
That's great. Thank you. So he's an archaeologist, Chapman C. Kajal researcher, and he's also a co-director of the Landscape Archaeology Research Group, Catalan Institute of Classical Archaeology. He is an honorary research associate, McDonald Institute of Archaeological Research, University of Cambridge. He was a member of the Trinity College Postdoctoral Society. He was a founding member of the Cambridge Computational and Digital Archaeology Laboratory. He is also a visiting lecturer at the Department of History and Art History, Rovira y Virgili University, that is in Spain. And he is also a founding member of a landscape archaeology research group. Moreover, he holds a PhD in classical archaeology with the honors. from Catalan Institute of Classical Archaeology in Spain. He got a DEA, which is like a master's degree from the same institute, Catalan Institute of Classical Archaeology. He got a bachelor's degree specialized in archaeology and ancient history. That's also comes from University of Valencia in Spain. So I welcome to Dr. Hector Oringo for your talk. So could you please take over the session for your talk? Thank you.
Thank you very much for the introduction, and thank you very much for inviting me today here. It's a pleasure and an honor. I just shared my screen. I hope you can see it properly.
That's right.
Perfect. So I'll start with the slides. So okay, so I'm as you said, I'm an archaeologist. But yeah, during the last 10 years or so, I have been very much focused on geoscientific analysis, GIS, remote sensing. And while I was in Cambridge, I did most of my postdoctoral career in the UK. And while I was there, I was in charge of the remote sensing and geoscientific analysis of the Two Range project, which is a ERC project, one of these big European projects with lots of people involved. And my job was, the project aimed to check the influence of climate change in the development and eventual disappearance of the Indus civilization, which you know much better than me was the biggest of the ancient world civilizations. And you know, and okay, we wanted to study, and it covers an enormous area. And well, so my job was more or less to try to develop methods to investigate the distribution of archaeological sites, their sizes, and how they relate to landscape changes. So in this presentation, I'm going to show you more or less the results of this research, which is still on course. We recently received a grant to continue with this research for another 3 years and try to expand this area you see here to the whole of the Indus civilization. But as you can see, this is a huge area, more than 250,000 square kilometers. And it's not that easy to access because it's a huge area and covers parts of India and Pakistan, and you know that we will never get enough people to cover such an area on the field. It's also a very diverse area with mountains, with irrigated agriculture, which always disturbs some of the remote sensing processes we are using in other areas, with desert, with large dunes. So it's a complex study area. Also, the irrigation channel network is very extensive, and this hides many of the features we are interested in seeing. In fact, for the development of this large-scale agricultural system of irrigation, they flattened out many archaeological sites that in this area form mounds. So, you know, if you have a mound in a field you want to irrigate, the mound will not allow the water to move. So we'll just distribute the water topographically. So in many cases, those are flattened. So it's a difficult area to work, let's say. So our objectives were to reconstruct the environmental conditions of the study area during the Bronze and Iron Age. And then to do that, we needed to detect and analyze archaeological sites in the study area, to find all the sites we can, analyze their size, their chronology, but and eventually be able to reconstruct this relation between environmental conditions, climate change, and the distribution of human settlements in the past. So being such a big and complex area, we couldn't use normal approaches in archaeology, so we moved to cloud computing, the use of machine learning methods, and multi-temporal and multi-source types of analysis. I'll show you how we did that. Okay, this is an image of the workflow, and which will also serve to illustrate this presentation structure, what I'm going to be talking about. Okay, as you see here in light yellow, you have the types of sources, for example, multispectral or historical maps, synthetic aperture radar, and then in dark yellow you have the sources itself, like Landsat, Sentinel, TandemX. Then in orange you have the methodological approaches, and in kind of red the methods we have been employing and developing for our analysis. And finally, in pink, you have the results we wanted to obtain. Okay, so you also have some two important things in gray, which is the training, how we get training data for our models and how we validate them. And I will divide this talk, and I will start talking about how we get to find the changes in the landscape. How we locate structures that can have influenced the human settlement. We call this archaeomorphology, but basically it's the detection of paleo rivers, ancient channels, ancient roads, all large-scale structures that can be used to analyze human settlement, mobility, and activities in relation with the distribution of sites. And I will start talking about this. Then I will move to how we locate data, training data. That is, which methods we use to know where there are sites, and apart from the sites that I already know, we use historical maps to find new sites, and we can use this to obtain training data for our large-scale machine learning approaches to the detection of sites. Okay, which will be the third section of the presentation. And lastly, I will talk how we validate these sites. How do we actually can check their chronology, their extension, their characteristics. Okay, so I'll move now to the first part, landscape reconstruction. And we had to develop a series of new methods because it was a very complex and large area. So we thought it was a good idea to start with multi-temporal remote sensing types of approaches. So we developed this seasonal multi-temporal multispectral analysis. In this case, it's been published in remote sensing. So you have here the reference in case in the lower right corner, in case you want to check it at some point. But the results allow us to reconstruct more than 30,000 kilometers of paleo rivers. I mean, what the image you have in here, it's actually only partial. We have moved a lot with this research, and now let's say we have been able to completely reconstruct the paleo river network of this large area. And this first approach, this multi-temporal seasonal analysis, use 30 years of Landsat 5 data, slightly less than 30, and we divide it into seasons, wet months and dry months. Dry month, we employ the statistical approaches like PCA and tassel cap transformations. That gave pretty good results for the location of paleo rivers. And for the wet months, we just use EV composites, enhanced vegetation index composites, and we created RGB composites during these wet months, and I will show you some of the results for this. But basically, we did all this analysis using Google Earth Engine, because it gives you direct access to all this data, so you don't have to download it or manage it. And it also provides the computational power, which is pretty important, because some of these analyses incorporated thousands of images. So those are the results of the seasonal multi-temporal multispectral analysis. As you can see, paleo rivers are very visible. In the case of the left image, this kind of pinkish image, we can locate paleo rivers. You see them here. They are slightly darker than the environment, because what we are locating here is the deposition of coarser sediments. during flooding episodes, and this reduces slightly the vegetation health. So this in the right side, you have examples of dry statistical analysis like PCA and TCT, and also very effective for the location of paleo rivers. And some of these are extremely clear and can be followed for hundreds of kilometers without, and you can actually reconstruct complete hydrographical networks. But obviously, all these approaches are based on many of these approaches are based on visibility, statistical visibility, and also health vegetation. Okay, and so we thought we should employ some other approaches in order to complete our paleo river network, and we developed this multi-scale relief model. We also obtained tandem X data, which is excellent. It's excellent topographic data, 12 meters pixel, although we sampled it, I think, to 25, because it was perhaps too much resolution. We didn't need that much for paleo rivers. And basically, this method consists on the development of several low-pass filter radios at different distances. So what you do is kind of cut the landscape on different layers and then reconstruct them together. Graphically, it would be something like that. Okay, and this provides excellent results for the detection of a small topographical variabilities over large areas. That might seem counterintuitive, but for example, we have features that could be very shallow, like paleo rivers. The difference in topography could be half a meter, but they extend over hundreds of meters. So you need a method that can at the same time locate very low topographical differences over large distances. And this method is ideal. In fact, if you compare this method with all other methods usually employed for microtopographical analysis, it's the only one that actually can provide a meaningful analysis of the topography. For your reference, image G is the MSRM we developed, and all the other images are other methods that are usually employed for the analysis of topography. The advantage of this method is that it's multi-scalar. So whereas some other methods like D and E can detect some parts of the paleo river network, then at some other points these rivers become smaller or become bigger, and and they fall out of the radius analysis radius of these other methods, so they are not good enough to create meaningful analysis of topographic differences over large areas. So, and I'll show you this is the results of the MSRM analysis for the study area, for this upper area, and I'll compare it now with the multi-temporal seasonal vegetation indexes. Here you see. So as you can see, I'll go back now. These dark rivers detected by the vegetation indexes, correspond to topographic elevations that are surely the levees of rivers created by flooding episodes. But this method is not able to detect topographic depressions, okay, because probably they were filled up with looser sediment and they don't have a decrease in these areas. There's no decrease of vegetation health. So the combination of these two actually allows us to complete the reconstruction of the whole river network. Okay, they work very well together, basically. And okay, this method also allows us to detect many ancient roads, many ancient mounds. I just thought the river was better for you to understand how this works, but it also allowed us to locate ancient channel systems. Okay, so now we move to the second part of the presentation, the extraction of features of archaeological interest from historical maps. That's how we went about for the location of many archaeological sites that we didn't know they were there. So we could create a good training data set for our automatic detection of algorithms. So we use the 1-inch survey of India maps. Okay, those are they started to be produced in the 1870s and they lasted until the 1930s. So they are previous to the large-scale landscape modifications of the 20th century, to the extension, for example, of the irrigation system. And they cover most of the country. In this image, you can see the maps we have been able to obtain, but we are actively searching now. We have agreements with the British Libraries and some Indian institutions to complete the maps of the study area. And in these maps, they are extremely interesting because thousands of mounds appear that have been flattened out. They have disappeared today. And therefore, they are a unique register of the archaeology of the study area. However, they are very time consuming. I mean, it's impossible to go one by one extracting every single mound that appears in these maps. Okay, it's very difficult also to cover the whole area systematically. Okay, many people just don't follow the lines and they leave parts of the map without investigation. There's also lots of inconsistencies in the features extracted by different people. So a manual approach was not feasible at all for the use of these maps to generate training data. So you have some examples here of mounds that are quite clear. So as you can see, there's lots of difference in the shape and the way in which these mounds are represented. So we develop different depth learning algorithms, mostly based on mask RCNN. We are trying some other approaches, but as our first approach, we went for this pretty standard approach. And for the different detectors we developed for the different types of sites, we got pretty high percentage success detection percentages, like 96%, 88%, with 4% false positives and 5% about 5% of miss sites. For some other algorithms, we reach 97% success rates with 3% of false positives, and in this case, in the second detector, only one site was missing. So that's how we generated our training data, apart from the archaeological sites we already knew. And then with this training data and the archaeological sites that appear in the literature and are well known in India and Pakistan, we could develop our multi-temporal and multi-source machine learning detection of archaeological sites. Okay. So how did we did that? How did we move to develop our machine learning algorithm? Again, it's a very large area. Okay, so our preliminary approaches, we saw that many mounts were relatively easy to detect with synthetic aperture radar because they had very different conditions to their environment. We actually tested this in the Cholistan Desert because it's an area that is very interesting archaeology. There's lots of sites, and some of them are, in interdunal areas. So thinking about our objective of how climate change influences human settlement, that was an evident area, very clear area in which we wanted to start, just to see how the desert affected the distribution of sites. So synthetic aperture radar in this area was a very good choice, but also multispectral imagery was giving some good results, but none of them was excellent. So we decided to join them and use a machine learning approach to analyze this data. Okay, so I'll show you more or less what we did. We employed the Sentinel-2 passive bands, okay, RGB and the red edge near infrared, and then the shortwave infrared. And then we used the Sentinel-1 with different combinations. And well, obviously we went through the processes like cloud filtering, removal of low intensity noise, radiometric calibration, and yeah, more or less for this area of the Kolistan Desert, we employed more than 1,000 synthetic aperture radar and more than 3,000 multispectral images. You know, that effectively constitutes big data. Okay. So we use our training data from historical maps, from survey, from archaeological literature, and in some cases, some very evident mounts that were visible in high resolution imagery. We trained our random forest classifier. We trained it in probability mode, and then we applied it. And this is the result in probability here. You know, some of them are very, very clearly visible, and then, you know, I'll show you some examples here. They present very variable shapes, and this is due to the interaction with dune systems and some vegetation on top, you know, because they tend to accumulate a bit of water. So, you know, a depth learning approach to find them was not very the best way to go. So, and those are the spectral signatures. As you can see, they are very clear. In red, you have the archaeological sites, yellow, the desert, green, irrigated areas, and in gray, all values, you know, that obviously cover the whole spectrum. So you see, like, it was surprising that Sentinel-2B12 band was quite discriminant, okay? But there are, they seem to be quite easy to discriminate the sites with this approach. In fact, here in purple, you have a LDA, linear discrimination analysis. You know, the biplot shows that in purple, the sites are clearly differentiated from other features. So with this approach, we were able to detect more than 500 sites, which we effectively multiplied the number of sites previously known, which, you know, this area was known for a high density of sites. Well, that was nothing. There were many more sites. More importantly, we found 4 new very big sites, which can be considered cities. I mean, the Indus had only 3 to 5 cities. So that was well, the most famous perhaps is Mohenjo-Daro and Harappa, but the new cities we found are not that big, but they come right after them. So this is really impressive, because it let us know that probably the Indus civilization was more urban than we have thought up to now. Okay. Another very interesting result is that the distribution of sites extends much farther into the desert than previously thought. Nobody went deep into the desert to look for these sites, but there are. You know, we only that means that probably the extension of the desert had a big impact in the abandonment of this area. Okay. So yeah, basically we with the results of the random forest probability, we had to apply a threshold, a morphologic filter, and then some vectorization. You know, I mean, you have here an image of the process, and in the top right, you can see a distribution of sites with, in yellow, the big new cities located. And you know, you have some stats here of the new mounts and the size, you see. But this distribution, it's actually, if you look what might be causing this particular distribution of archaeological sites, is pretty interesting, because if we are not locating sites in areas of irrigated agriculture, so we will need to develop new classifiers for irrigated areas. And the ones we are located in the desert, you know, here in white, the high values are actually deep dunes. So we are only finding sites in interdunal areas or areas in which dunes are really not deep. That means that the distribution of sites we have found, it's probably a small part of the number of sites in the area. Most of the sites must be lying under the desert dunes. So we really might have had here a very important and central area of the industrialization. But yeah, I mean, despite of the success of this algorithm, we let's say this algorithm is not applicable to other areas. So in order to move to areas with more vegetation, irrigation, we have to improve it, and that is how we are going about it, including thermal and infrared, including new types of active sensors, but also most importantly, the derived products. I think the sources we are including in our models are really important, as they are the only way that allows us to actually focus the analysis on our features of interest. For example, I think the seasonal multi-temporal vegetation indexes are very important because we have realized that archaeological sites have in general a lower agricultural productions than areas that do not have archaeological sites. MSRM, it's also a very good approach, since even when you flatten a site, the central area is still a few tens of centimeters above the average of the ground around. So, if you join all these derived products in your analysis, you have new ways to employ machine learning to locate sites in areas that would have been very difficult using just the raw sources. So we have made some proofs with this new type of analysis, okay, trying to develop a kind of continental scale mount detection algorithm. And we use the fertile crescents because it's an area we know there's lots of sites, we have lots of information, so it's easy to select training data and easy to test the results. So we choose a very large area just to see how it would perform, and those are the results. You probably are thinking that you cannot see anything here, but we are really far away. So if we zoom in, we start seeing some kind of speckles on paper, and here you start seeing what the algorithm detects at high probability archaeological sites. Okay, if we zoom more, we have here a very clear image, and let's zoom even more so we can go into an individual level. Okay, this is an image of the. I don't know if you can see my arrow, but okay, this would correspond to this archaeological site, to this mound. Okay. And this is a very interesting case because you see this high probability area in white does not correspond to the modern city, but to the surrounding of the modern city. You see, it's very interesting. So what we have here is a mound with a relatively modern city on top of it, town more than city, a small village. And this is another interesting case in which we cannot see anything visually, but with some analysis we detect some features that correspond to the high probability areas of the random forest classifier. So this is all very good. This will allow us to make incredible progress in the detection and protection and understanding of archaeological sites in the next few years. But what about those sites that are not visible anymore? Those that leave no trace in the bands that we are employing? How do we usually go about this? Archaeologists, we usually employ intensive, extensive pedestrian archaeological surveys. So you usually have teams of archaeologists, tens of archaeologists walking the fields and looking for remains of pottery fragments, because this is the most common find in archaeological sites. And if you have concentration of pottery sets or what we call pot sets, it's usually because you have an archaeological site below. But obviously, it's very costly. You need lots of people working for many years to obtain high quality quantitative data. And you usually do not record all the pottery fragments. You just record things like density. There are lots of them here, or so it's difficult to compare different surveys and see, okay, this area has more density of sites than the other, or the sites were more occupied, or they were bigger. So this makes this kind of field approach a very long-term business. So for this, we have been developed some kind of drone-based automated archaeological survey methods. Basically, it's just it's very simple. It's a drone with a high-resolution camera flying above the grounds of the areas of interest. Okay, and depending on the density of the images, you can do create ortho images that you can use photogrammetry approaches or SLAM approaches, and then use a machine learning approach to extract the the podsets. And this has, in this case, you have some examples here. I mean, and this we published the first paper about this in 2019, and now in a few weeks, I hope our new paper will appear. We started using random forest and some other classical machine learning approaches, and now we have moved to deep learning, because if you have enough training data, you can really, I'll show you the difference between random forest and deep learning. Okay, deep learning detects more, but also it defines better the shape of the pod cells. So it's very useful for us. And you have examples of fields in which we have been able to detect individual pod cell shapes, and created densities. We can even use these ortho images, the vegetation, to filter out the density of pottery, which would make comparisons between pottery densities in different areas possible, which is something relatively new. You can also use the pottery size, the straightness of the edges of the pottery, their orientation, to make interpretations about site preservation, central point of the site, site size, different types of sites. So this is a whole new world for archaeological survey. If I guess it's in a few years this will become a standard practice. So as a conclusion, since I'm almost reaching my time, this is a very exciting moment for the geosciences. We have a large accessibility of sources, repositories. We can access also large computing resources, and we have new ways of data capture. I mean, there are new drones. I mean, when we started this project, the automated detection of podsets, the drones available are we're flying a fraction of the time the new drones can fly with much worse cameras now. It's going very fast. Okay, so all this amount of data and processing powers allow us to create virtual constellations of multi-source and multi-temporal data, which can only be meaningful analyzed with machine learning approaches, mostly when you are working on very large area. Okay, so I think this will make enormous changes in archaeology, but also in many other geoscience disciplines. So thank you very much for your attention, and I'm open to questions if you have any.
Thank you very much, Dr. Hector. That was a great presentation showing all the archaeological sites and how you can bring all that together into your machine learning, especially on your multi-temporal to multi-source machine learning ways. That was a great one. I forgot to mention about one of your achievement. That was a Journal of Archaeological Science and Society of Archaeological Sciences Emerging Investigator Award for 2019. That was a great achievement. So thank you very much for presenting a good presentation. So yeah, we will now look for some other questions. Can you read some of the questions in the chat box?
Let me see. see if I can access the chat box.
Can I ask a question?
Oh yeah, here it is. Oh,
Yeah.
yes, of course.
Actually, I'm talking from, my name is PJ Cherian. I'm talking from Pattanam Archaeological Site. So this site is actually one of the important discoveries in recent times about a port site. So that was a very significant one in the early historic period, that is from 5th century BC to 5th century AD.
Wow, that's a very nice period. Lots of Roman commerce, I would imagine. Lots of Roman amphora and Greek.
Yeah. But you know, the basic problem is we haven't identified many contemporary sites in the area, or we have a big problem, lacuna of historical information, because this was lost for last 2000 years. And once it came to light, you know, we have an attitude to isolate and see that it is not connected to the historical phase of the times. And therefore, the kind of presentation was indeed very helpful. And I was wondering, we are about to launch a surface survey, which you called as pedestrian survey, in the two river basins of Chalakudi and Periyar. That is, we are located in the river mouth of Periyar, and the adjacent river is Chalakudi. So I was inquiring about the possibility of having some potential collaboration. You know, we are collaborating with Christ College, a co-host of this event. And we had also excavated a site 17 kilometers to find out whether this main site, Pattanam or Musiris, have any links there. Unfortunately, we could not find any direct connections. And so we are in a stage where we thought that this pedestrian enquiries for subterranean traces is very important.
Yes.
And we are trying to make it. But I think a collaboration, a kind of a consultancy with you people can really make it to the other extent of identifying more sites in this coastal region.
Yes, obviously, yeah, I would be very glad to collaborate. I mean, these methods are published, but we obviously are pushing forward the technical aspects with new drones and stuff, and we will be glad to try them anywhere, of course. In fact, some of my postdocs, like Francesco Nessa and Arnau Garcia, are you know, they are collaborating with many Indian and Pakistani institutions. And you know, yes, of course, just drop me an email whenever you have time, and we can continue this conversation in person and check possibilities of collaboration, of course.
Thank you so much. Thank you so much. In fact, I know them. When they were in Kerala, we have met.
Yes, recently. Last summer, just before all this crisis happened, when we could still travel. Good old times.
Thank you so much.
Thank you.
Thank you for
thank
your
you, Cherian, for your good comments and a collaboration inquiry with Dr. Hector. That's a great
Should I ask some of the questions I see in the chat?
Yes.
Yeah.
Okay, so I will answer this one because it's a classic one. How from that from 1984 onwards, we can go down to make interpretations of you know, thousands of years before. Well, actually, landscape archaeology can only look at present time landscapes, but these ancient uses and ancient activities leave marks that can be seen today still. I suspect the question is more related: how can we know these rivers were active at different periods? So this is relatively easy to well, relatively easy. It's a very complex question because some of the ways we use to date are very difficult, but the typical approach is to check the sites around and see what are the chronology of the sites that statistically can align with these paleo rivers. Okay, that usually when you have tests like the Kolmogorov-Smirnov, that would tell you the statistical significance of a series of sites being aligned with a lineal feature, in this case paleo rivers. So, and in fact, our multitemporal approach is not really is not really trying to go back in time. It's trying to get more consistent data. If you use 30 years of data, you get rid of different types of cultivation that lasted 1 year, and you get an image of vegetation health that is very consistent. So, that's why we use multitemporal data, to avoid the effects of specific environmental circumstances. And I don't understand very well this question about how histogram equalization and PCA works on image differently. I mean, these are different types of analysis, and histogram equalization, we use it mostly for visualization purposes, and PCA is a spectral reduction technique that allows us to analyze large quantity of layers in meaningful ways, just creating RGB composites. So basically, I don't know if I have answers.
Yeah, I mean, even that's fine. Like, I mean, Ajay, could you please send Hector an email so that
yes,
you
yes.
can get better.
Everyone in meeting. Yeah.
Hello. Can I ask a question?
Yep, you can. You can
Yes.
go for
Yes.
a better, please.
Yes, it's Nkanyiso again from South Africa. Dr. Hector, I just want to ask you, have you considered using support vector machine as well, and maybe classification and regression model, CAT, just to have several of these
Yes.
machine learning systems? I know that random forest always gives me better results than the two, actually, when I do my land cover classification here inside using Colab or Google Earth Engine images and Google Earth Engine JavaScript.
Yeah.
So I just want to know, have you tried that? And also maybe one more, why don't you consider you looking at before you do this classification, you use something like pixel-based and object-based land use, land cover classification approaches. It should give you an improvement in your results. I've done that before, and I saw that it gives better results. And what I normally do is I do that on 3 machine learning approach, which is random forest. I also use CAT and support vector.
Yes, excellent question. For our Cholistan site detection, we made tests with different approaches. One of them was actually super vector machines, because it's also implemented in Google, and and it worked better. Random forest, I imagine, because it's it's a weighting method basically. So out of practical results, we went ahead with our large scale analysis with random forest. But you are right. For the global scale algorithm, the one I showed before, yes, it had a preliminary classification, or a kind of unsupervised classification using cards to select the areas in which to apply the random forest. And this provided much better results, because then you are much more consistent on the application of machine learning on specific situations, because you divide the area, you get a preliminary classification of environmental variability, and you then can use specific training data in specific environmental circumstances. So yes, this preliminary approach of doing unsupervised, because when you are using that amount of layers, it's very difficult to have a clear interpretation. It's very difficult to say, okay, this is a type of environment. It's very difficult to use supervised classification because there are so many layers that you cannot understand in conjunction, like the thermal, like the synthetic aperture radar, the multispectral, that if you define yourself, if you do a supervised classification, you are probably prioritizing your own eyes, your own, the visible bands. So when we have done this, we have used an unsupervised classification to divide the area and then applied the specific training data for one of these automatically classified areas. The results are much better. That's why we had such excellent results in an area that is so large like the Fertile Crescent, because in reality they were lots of small analyses adapted to specific circumstances. I don't know if I have answered your question, but I can see we are thinking along the same research lines here.
Oh, yes. It's fine. It's fine. No problem. Thank you very much, Hector. Yes.
You're welcome.
Thank you, Mr. Bhatta. And there is a extended question from JN in the chat box. Can you read that, Hector, please? If I may.
How can one? Oh, yes. If I may explain the question, how can one be sure the river traces we find related to say 1,000? Yes, we cannot be sure. It's impossible. I don't think. I have been reading a lot about the subject, and we collaborate with Oxford, with the geography department, which has people that are specialized in dating paleo rivers, and I don't think the results of OSL dating are reliable at all. Okay, so what we can be sure is that we can do a stratigraphy of the landscape. I mean, when you create a network with the whole hydrographic network of the rivers, you can see that some of them need to be previous to others, because if they cannot exist at the same time, because if you have a river that crosses another, the water would move. So you can divide these rivers and create a kind of relative stratigraphy of which ones go before others. Okay, and some of them can be for some of them we have very intensive surveys in the area. Okay, so we know we have hundreds of sites, and we know how these sites relate to these rivers. And in some cases, I saw this. Let me show you if I. Yeah, let me see if I find it. But we have this. Okay, yes, this river here. Okay, between Nohar and Hisar, we have found several hundred sites, and they are all perfectly aligned with this river, and they all correspond to a specific period of time. So we cannot be sure, of course, but we have good hypothesis that this river was active at least during this period. We know it was active also during later periods, but at least we can hypothesize that some rivers were active during periods in which we have a significant number of sites close aligned to its course. That's of course we cannot be sure, but I think it's a good approach, and then it needs to be tested, of course. But yeah, that's the main approach we use.
Thank you, Hector. I hope Jane satisfied with your answer. Otherwise, I mean, shoot an email to Hector and find out.
Yes, I'll be happy.
Yeah. Thank you once again. Thank you very much for your good presentation and question and answers time. So on behalf of the organizing committee and myself, say a big thank you to you. So
thank you very much to you for inviting me.
With that, I will hand over to Dr. Lindo for concluding remarks.
Hello, am I audible?
Yep.
Yes.
Okay, thank you very much. It was very nice talk we had today, 2 sessions. Though we were having only 2 talks today, we also had a number of participants logged in with us. So tomorrow we have a longer session, as it was already told by Dr. Manacheri. We will have 5 sessions tomorrow, very interesting, with big data analysis and artificial intelligence in geoscience, then advanced stratigraphy and sedimentology. I request all the participants to tune with us tomorrow at 3:30 Indian time or 10 o'clock at UK time. So I hope you had a very interactive session today, and I'm sure all the students, especially those who are attending this program, must have found it very useful and interesting. And our resource persons have shared their details. We will be giving to you. If you have any specific questions, you may interact with our resource persons today. Thank you, everyone. Thank you, Dr. Saju, for the time. Thank you.
Thank you.
Thank you. Bye.
It's time to wind up the session. Let me take a while to thank our session chair, Dr. Saju Menacheri, for running the session very well. And a reminder for the participants, the feedback link is provided in the chat box. Kindly fill it. And tomorrow is the final day of our colloquium, so we expect your active participation tomorrow. That's all. We'll see you tomorrow. Bye. Thank you.